Welcome back to Algebraic Geometry. This is the third video, and in this video I'm going to talk a little bit more explicitly about z of t and I of u and some correspondences that are noteworthy. So just to recap, z of t takes chunks of functions in the ring. Remember, the ring A has all the polynomials, and it associates with that chunk of functions t a set of points in the affine space, and the association is just where all of those functions are zero. Okay? On the other hand, so just as an example, maybe two functions, f is x and g is x squared. Well, then if I were to find the zero set of this, it'd probably be like x is 0, right? And maybe even y is 0, depending on how I'm looking at it. Okay? I of u, on the other hand, that takes a chunk of the affine space, and it associates with that subset of the affine space a set of functions, and in fact an ideal of functions. And it's easy to see that this is an ideal, right? Because if I take some element of the ideal, this function f has to be 0 on all the points in U. And so if I grab, pretty much any other function in the ring and I multiply g by f, and I restrict it to U, I'm still going to get 0, right? Because this still has that f in it, that g times 0 is going to be 0. So this is in fact an ideal. And as I sort of mentioned before, you can think of this map Z, you can think of this function-like thing, I'll call it. The inputs are sets here, so it's not really what we classically think of as a function on sets. But you can think of this mapping Z as taking something from A, or some things from A, some collection, and sending it to something in A in the affine space. And similarly, you can think of the ideal as taking some chunk of the affine space and sending it to some ideal in the ring A. So this leaves a lot of things to think about. One of the immediate things you might think about is, well, what happens if I were to cycle through this? It seems natural to think, well, okay, I'm starting at A here and going to A in, but then I could take I and go back to A, right? So if I started with something, let's say in A in some set U, and then I hit that with I, and then I hit that ideal with Z, what do I get? And similarly, if I start with something in the ring, let's claim that it's a set. Let's just be easy about it. It's T. And I hit it with Z so that I'm here in this space now, the affine space, and then I hit that again with I. What do I get? Well, these questions were really the focus of a pretty important, I guess you'd call it, theorem in algebraic geometry called Hilbert's Nullstellensatz or something. I don't really know how to pronounce it. But what I'm going to do, Nullstellensatz maybe? I don't know. Anyway, I'm going to show you what the answers to these are. I'm not going to go deep into the proof, but then we're going to look at some things about them that are pretty interesting. We'll start with this one. Now, if we imagine that T is an ideal in A, and we hit it with Z and then we hit it with I. So again, what are we doing? We're finding the set of points in A in where all the functions in T are 0, and then we're finding what the ideal of that resulting set of points is. What we get is somewhat surprising. We get the radical of T, T being an ideal. Now the radical is something you may or may not have seen before. Here's the breakdown of a radical, and I'll do a quick example using integers. So basically, the radical is every element inside the ring such that some positive exponent of that element is in T. Here's an example. I have in my possession an ideal 12z. We know what this looks like. It's just 0 plus or minus 12 plus or minus 24 plus or minus 36. And I am tasked with finding the radical of 12z. Well, note that I could just choose 1 for this. And then I know for a fact that 12z is in this radical of 12z. So the question isn't really, is it the same, so much as it is there anything else in there that I could find is the exponent of something. And without getting too rigorous, I just kind of glance over. I say 12, well, that's not a power of any integer. 24, that's not a power of any, oh, wait, 36. 36 is 6 squared. So I have that 6z is inside the radical of 12z. I know that the whole ideal's inside because if one piece of it's inside, I could run through by the whole ring and I'd have to get the whole ideal. So with a little more work, you can actually find that 6z is the radical of 12z. Another example, I'll pause it for a second. Another example using the integers, I always find that the integers are the easiest ones to look at. I think that's pretty obvious, but it's easy to get these ideas down using this that we're so familiar with. 15z, so here we are, we're looking through the ideal just like we did before. Again, we know that 15z is inside the radical of 15z. And I put the element there, I meant to put the subset sign, is inside this radical, okay? Because I could just choose 1 for an exponent here, and then all a and t are naturally in the radical. But here's the question, more to the point. Here, if you'll notice, 12, right, 12 breaks up as an integer into 3 times 2 squared. Now 15 breaks up into 3 times 5. 3 times 2 squared, and I'm asking myself, well, am I going to get something that's a to the n? Well, if I multiply this by 3, you can see, times 3, I get 3 squared times 2 squared, which is just 6 squared, right? So that's actually how I got this ideal. The problem with 15z is that 15 is 3 times 5. So the next number that I'm going to get that is an exponent is when I multiply by 15, which is not going to change anything about the ideal. So it turns out that this ideal is in fact its own radical. So if we had just some set t in here, we would consider then the ideal generated by t over here. And just one thing to note here, although there will be more a little bit later on. If you have a prime ideal, j, then naturally j is going to equal its radical. In other words, it's going to be what we call a radical ideal. If you have this condition, then we call j a radical ideal. I won't prove this, but an easy way to think about it is, if we have a to the n in j, and j is prime, then that means that either a or a to the n minus 1 is in j. If a is in j, then we're done. If it's not, then we just do it again. A or a to the n minus 2 is in j. And we continue until we have a or a is in j. That is all I'll say about that right now, but we'll be coming back to this shortly. So let's go back to this formula for a second and use what we just learned about prime ideals. If j is a prime ideal in A, then I of z of j is just j. Now recall what I said in the last video about I of u union v. This is the intersection of iu and iv. So think about this for a second. If z of j, so suppose z of j is some proper union of sets u1 and u2. If this is true, then I of z of j is a subset of I of u. And it's also a subset of I of v. I don't know why I picked different letters for this, but whatever, that's okay. Could have said u2. Anyway, the point is, this would be smaller, right? This would be a smaller thing than I could get from just if it was one piece, which gives you this intuition that maybe there's something special about z of j, and it turns out there actually is. Z of j, when j is prime, is an irreducible set in the affine space. And we say this in terms of the topology that we'll talk about shortly. It cannot be represented as the union of two proper subsets. One other thing that I want to mention here is this idea of descent in the topological space. So if I have these sets, let's say U1, that contains U2, that contains U3, etc., all the way down to a point, right? So this would be the smallest set in this affine space without being the null set. It would associate with an ascending chain of ideals. IU1, IU2, IU3, all the way up to the ideal associated with the point. This would not be the entire set because this is a proper subset. So it has to be a proper ideal of the ring A. However, there cannot be an ideal between this ideal and the full ring. So this is a maximal ideal. Okay, so that gives us two correspondences, which I'll just draw out really quickly. Now notice that I did have to assume that the ring and the topological space are noetherian. If you don't know what that means, you can look it up. It just means you have a maximum element in an ascending chain of ideals. But yeah, these are the two big-time correspondences that we land at the very beginning of this thing. And notice kind of the cool thing about this. These are members of the ring, right? These are algebraic things, right? These are just algebraic things over here. And these are, of course, these are sets. These are points, right? So this is geometric stuff. So we have these correspondences between algebraic things and geometric things. And this is kind of the beginning of the whole story. Prime ideals and irreducible sets, maximal ideals correspond to points.